value that was in some of the earlier slides would be basically the break-even point. So in other words, if Q is greater than 1 or much greater than 1, that means we're above the break-even point. And this is the idea that, okay, the energies of these ions have to be in this range or higher in order to be able to, say, overcome that Coulomb barrier. Again, a lot of it is just that you actually have quantum tunneling taking place, but nonetheless, just to get high enough in the barrier to be able to have some reasonable tunneling probability, you have to have this amount of energy. And so this criterion is easy to write down, but it's actually very difficult to actually attain in practice. So here is I would say, the most widely used scheme that's been tested over and it's scaled up further and further over the years. It's in principle, it'd be easy conceptually if all you had was a toroidal field that went around like this. But it turns out you have to also have another component of the field that kind of does some wrapping around in some funny way, if I remember correctly. And I think what happens is that if you go back to your 1322 class, any charged particle in a magnetic field is going to have some kind of helical motion, and if it has let's say it's moving along this direction, and then if you combine it with having some helical motion, I guess the idea is that the bigger the magnetic field, the smaller the helices. But the idea is that how do you keep this thing from blowing apart? I guess that's the question here. In other words, how do you keep this plasma from just completely blowing apart, and then that's it? You can't contain it. And so I think what they do is they have like this funny loop-de-loop combination of helical motion, like a double corkscrew, I believe, where somehow the plasma is able to, in principle, contain itself, except in practice you get all kinds of instabilities that they find. And apparently, in order to really, with a conventional tokamak, to get it to be stable enough, they keep having to scale it up more and more and more. And so the next one, which is being constructed right now, is called the ITER, which I wish I could remember what that stands for. I think it's something like International Tokamak Experimental Reactor, I believe, something like that. This is being built in the south of France, right here. The cost is humongous. It's I think it's in the tens of billions of dollars. So this is going to be a very large tokamak reactor. The idea is that the size is big, the size of the magnetic fields is quite large. I think maybe around, I don't remember exactly, 10 Tesla or thereabouts. That's the other irony, is that because the magnetic field has to be big, you have temperatures around 200 million degrees inside your plasma in here. So it's like a magnetic bottle. You have to have pretty close to a vacuum, clearly, between the magnetic bottle and the rest of the surrounding material. But then out here, you actually have to use superconducting magnets, which would be typically cooled with liquid helium, which would be around 4 degrees Kelvin. So you have an enormous temperature gradient getting from here down into here. Now, again, how do you get the things that you need to be able to fuse, like tritium and, well, I guess let's say deuterium and tritium. Deuterium you can extract pretty readily from water, so that there's a certain amount of that in water. You can make so-called heavy water. The tritium, I guess what they do is you would actually probably regenerate some tritium by having a lithium blanket, because you have a bunch of neutrons that are emitted during the fusion reaction. So you use that to convert some of that lithium, these two guys, into a certain amount of tritium, which are these two guys right here. And so then you could actually somehow recover that. I guess you would actually recover this tritium and then use that in the actual reaction right there. Now here's some interesting proposal. I mentioned that the ITER has to be absolutely humongous and actually horrendously expensive to be able to build this. Now, I want to point out that one of the limits on how big a magnetic field you can get with a superconducting magnet, which I may have discussed in some earlier slides when we were talking about superconductivity, is the upper critical field limited by how many vortices can you cram into your material, flux vortices. That upper critical field for a low TC, let's say a good low TC material, might limit your magnet size to, let's say, about in the range of 18 Tesla, somewhere in that ballpark. Guess what? Well, and that's really pushing it too, to really even get up to that field. And let's say at a larger scale, maybe around 11 Tesla perhaps. Well, it turns out that one of the other potential advantages of the cuprate high TC superconducting materials, aside from high critical temperatures, is they have incredibly high upper critical fields. They're so high you can't even measure them. So if you extrapolate, you can estimate that YBCO's upper critical field at low temperatures would be maybe well above 100, like maybe 160 Tesla or way above 100 Tesla. So that means if we make further progress in making good HTS tapes and cables, then you could start to make magnets that might be in the 30 Tesla range, for example. You wouldn't actually operate at liquid nitrogen. You'd say, I'm going to keep pushing it down to liquid helium. But what I'm going to do is I'm going to go ahead and take advantage of the high upper critical fields instead of taking advantage of the high critical temperatures. And then when you do that, by pushing the magnetic field, let's say up to around 30 Tesla, or even in the 20s, let's say 25 Tesla, you could then take this thing that they're building in France and scale it down. It would still be expensive. It might be 300 million, but it'd be 300 million versus 40 or 50 billion in terms of cost. And so there are several schemes that have been proposed along those lines. There's one group at MIT, that was a bunch of students as their class project. For this class, they actually proposed a scheme that would be involving making some high TC, a tokamak using high TC magnets and tape, using tape. There was another scheme called the spherical tokamak, which is something that's being studied in England, I guess. They built actually kind of a version of the spherical tokamak, I believe, but not quite in the high enough fields to reach the break-even point, but still, that's another scheme that's been proposed. And so within this tokamak framework then, I think that high TC superconductivity, if we could get the research dollars to actually push this forward, could have potentially a major impact. And again, the advantage of fusion over other forms of nuclear energy is that you're relying on essentially mostly water, but I guess some lithium. But lithium is also quite abundant, so it's much more abundant than the things that we have that we would need for fission reactions, for the overwhelming majority of fission reactions. And then not to mention that you're not creating a lot of radioactive waste products. I mean, I guess there would be a little bit of radioactivity in the shielding around here, but it wouldn't be nearly the big problem that you'd have with the conventional fission reactions. Now you have to heat these plasmas up, so there's other things like RF induction heating or other schemes that are used in order to get that plasma up to the high temperatures that are needed to attain the fusion reaction. Now, there's another scheme, another whole class of schemes, which is based on this method called inertial confinement. The idea is that, well, we're just going to try to have it fuse for a short period of time before it blows apart. In some ways, that's what a bomb is, really. A thermonuclear bomb is kind of an inertial fusion reaction where it just stays together just long enough to fuse, and then it blows apart, but you get the energy out. And I mentioned, well, the problem is that with your conventional fusion bomb, there's a lower bound of how small it can be. It's, small enough to destroy the Texas Medical Center, perhaps, but maybe not small enough, but maybe not big enough to wipe out the entire city of Houston, but still bigger than what you'd like to use for a practical device. So that's what, in principle, that's what these inertial schemes are. Would be, well, is there some scheme where you can make little tiny micro explosions, more or less? And so this inertial